Hi, my name is Jack McCluskey. I'm a software engineer at Google working on Dataflow and Apache Beam. And I'm here to talk about making the jump from batch pipelines to streaming pipelines, the motivations behind why you'd want to do that, the concepts you should be familiar with before you get started, things along those lines. Importantly, before we get too far into this talk is going into pretty general data processing concepts for streaming. We're not going to be touching on how you use these in Beam specifically and how you interact with them in this talk. If you're familiar with these things and you'd rather just see how you use them in Beam, there's a follow-up talk to this called Making the Jump from Batch to Streaming Beam Primitives. Go check that out for more specifics on how Beam interacts with these concepts and some Beam-specific concepts for streaming that we will use. Okay, so why make the jump to streaming? So two relatively common streaming use cases are that you want to process your data in real time. You'd rather get things as they happen. Or a really common case is you have a batch pipeline that you find yourself running more and more frequently. So it could be you run this pipeline once a week and suddenly you have more users and data. And so you need to run every day. And then suddenly it's twice a day. And then eventually the intervals where you have to run them are so tiny that you're better off running a streaming pipeline. This is a surprisingly common way for people to back into needing streaming. But fortunately, Beam lets you use very similar semantics for streaming and batch. It's a unified model, so it's very convenient. But there are differences and conceptual differences that are very important for how your pipeline operates, how you have to reason about what you're doing, things like that. So something to consider initially, you are looking at bounded versus unbounded data sources. So batch pipelines really operate using bounded data sources. You know exactly how much data you have to process at the start of the pipeline. Any sort of division of labor, any sort of scaling, parallelization is a matter of dividing a fixed amount of work. You have some number of elements that you're processing. You can shard that out into however many workers you have, and that's very straightforward and simple. Streaming pipelines ingest data from unbounded sources. You actually have no concept of how much data you could potentially read. It's theoretically infinite. Data can arrive out of order. It can arrive late. You're dealing with something that is far less knowable conceptually. So you have to account for that. But that is a major starting point here. Bounded pipelines are also visually very simple. You have on disk or from some source some amount of data here. And then you run your pipeline, and now you've done some transforms, some sorting, some aggregations, what have you, and you're back into your sink with your data transformed in some way. We have this nice organized visual here. Unbounded pipelines are, of course, more complicated. We have some stream of data coming in, and when you run your pipeline, you're organizing into discrete units along that stream with some measure of how they're split out. So you see chunks of that stream are being organized as you go. And then processing pipelines, you have batch pipelines where you're generally dealing with pretty steady throughput. Each transform should take around the same amount of time. Of course, laggers and stragglers can happen, but for the most part, you have large bundles being processed at the same time. You have a pretty steady stream from start to finish. Streaming pipelines have variable data throughput because you could get more or less data at any given point in time. Periods of high activity, low activity, things like that. So you have varying computational needs over the life of your pipeline, and you're processing 1 to 2 elements at a time, usually, at least in the Beam sense. You're doing 1 to 2 element bundles at most, whereas in batch, you're ideally looking at much larger bundles being processed. Now for the big concept that I think can be used in batch, but is truly essential to streaming, processing in time. So 2 bits of terminology here. Event time is when the data being processed was created, the actual event that led to data creation. It's a timestamp, naturally. Whereas processing time is when we're actually processing that data in the pipeline, when we're actually doing our transforms, our operations, aggregations. Ideally, we want this to be the same time. We want our event time and processing time to be one-to-one, true real-time processing. The problem with that is that there's always going to be some delta. Just conceptually, you can't always instantaneously have data from different sources immediately in your pipeline. You can have data that arrives late or takes longer to get there. We are constrained by the speed of light at minimum, so there's always some delta. And so this is a good visual for this. You have your event time as your x-axis and processing time as the y-axis. And in reality, the distance between processing time and event time as far as the ideal can vary. You can have a lot of data coming at once, and then your processing time is going to start to lag behind a little bit. And then you can, catch up, and then suddenly you get an element, you process it as fast as possible, and you're relatively close to the ideal. 2 quick things to call out. The gap in the processing time compared to the ideal is called processing time lag, and the gap in the x-axis of event time to the ideal is event time skew. It's really just trivia. You might see those terms on occasion, but something worth knowing. Okay, so now let's talk about windows. So when we were talking about these streaming aggregations that we were looking at way back, we had that continuum of a streaming source, and then we had cut it into chunks. Those chunks that we output are windows. Windowing is the process of slicing up a data source based on time. To be clear, when we're talking about time here, we're talking about event time, not processing time. We're aggregating data as it happened in the real world, not as we're processing it. That does come with some complications, but Beam makes it easier to deal with that than you might think. That'll be on the next talk, though. There are multiple approaches that can be taken for windowing. Quick overview here, as I'll get into a little bit more in the Beam specific talk. The global window or global windowing, you'll hear that referred to a lot. You are talking about truly everything from Unix timestamp 0 to the maximum Unix timestamp existing in a single window. This is a relatively easy abstraction. Everything is just in the same place. Then for more useful slices, we have concepts of interval windows. And those are, you're looking at from timestamp A to B, that is a window, and you continue that on and on. The 2 variations of that are fixed windows, where the length of the window and the period in which windows occur are the same. So you only have one window from A to B, one window from B to C, etc. Sliding windows have a period less than that interval, so you get overlapping windows, hence the sliding, where they just go repeatedly on and on. Very good approach for including a more gradual changes in your data. You can also, at that point, you have elements that are in multiple windows at once. And then one that comes up on occasion is the concept of a session window. This is a window where you are trying to encapsulate a series of events that happen close to each other. So the idea is you actually have a series of sliding windows set based on when events are happening, and then you merge them together to create bigger windows that are supposed to represent events happening within a session. I think the clear example of this is like if someone is browsing on the internet and they are clicking things and you're tracking events across a website, you may care if a user is on your website continuously for like 10 minutes and then they leave, and then that 10-minute chunk is one session, and then maybe they come back later and you can get another session out of that, etc. A little in the weeds there. It's a little specific for use cases, but good to be aware of. Okay, so now we have data in windows that are, aggregating that data. How do we know when we have all of the data for a given window in a streaming pipeline? The short answer is we cannot know for sure. So the watermark is a concept of how we represent the latest event time for which we believe we've ingested all the data for. Mechanically, the system thinks that it will no longer get any data from before the current time of the watermark. The watermark is monotonically increasing. It can never go backwards. It is just an estimate. So here is a good little visual for how watermarks work. We have a series of elements that we've gotten. We can show when we're going to get them in processing time and when they actually occurred in event time. And then that green dash here is going to represent the watermark. So first, we're going to start talking about a perfect watermark. This is a concept in which we always have perfect knowledge of the data we're getting in. And so we will never have the watermark advance past an element that we are going to get in terms of event time. So we have our windowing and event time sort of loosely put in. The thin black line is where we are in processing time. And the watermark is our dashed green line, showing that we are still accepting elements. We think we have more elements that will occur sooner in event time. We process more. We've gotten more elements. We've put them in new windows, but our watermark actually hasn't advanced past that sort of lagging element in terms of processing time. But once we clear it, we start to advance the watermark. And then as we have data, we actually emit these windows in processing time. We consider them complete because we are convinced that we're not going to get any more data past this point or from before this point in the watermark. So we can emit all that data and we think it's complete. But here's the problem. In a perfect world, we would have that knowledge and we would be able to do that mechanically relatively easily, but we can't. Watermarks are generally determined through heuristics and estimation. So instead, we're going to look at a heuristic watermark and show how that behaves on the exact same data. So similar things, our watermark is this solid green line now, and we have two windows that we are currently have data for. Our watermark has advanced past this first window of data, so we think we're going to emit it. And then we continue on processing, we get more data, and our watermark continues to advance. We've emitted the second window and this third window, but we haven't gone past the end of the last window here. And then we get more data and advance our watermark. We have this last window emitted with all of its data. Everything is relatively similar, apart from this one red bit of data that we got later. This is now considered late data in our streaming model. So our system has blown past the event time and has emitted data and thinks it's done. And now we get data that's late. What do we do with that? How do we conceptualize dealing with this? So when we get late data, which is from before where the current watermark is at, how did that happen? The real world is messy. Data can be delayed for a number of reasons. One of the most common examples is the idea of your application is processing data from a mobile game on your phone. It's getting high scores from users and updating the leaderboard in real time. Well, say someone gets on a plane and is playing their game on airplane mode. You're not going to get their data from their flight. Could be a little bit behind, could be a long flight. You're not going to get their data from that flight and the games they played until they land and they turn their phone back on. So you're getting that data late sort of inherently. But various things can happen. Like I said, the real world is messy and we have to account for that. So our pipeline does need some rules on how to handle late data, which we have questions to answer. How late will we allow data to be? Will we include late data at all? And these are considerations that largely stem from how complex the operations are operating on your window. But we can get into the specifics of how Beam does that and how you configure that within Beam on the next talk. We're going to talk about the primitives. We're going to talk about the concepts in Beam, how you implement them with some code examples in Java. And then we're going to get a few examples and explanations up there for you. But real quick, I do want to plug a little bit of extra reading if you are interested in these concepts. Streaming systems, the what, where, when, and how of large-scale data processing is sort of the book on batch and streaming processes from the perspective of Apache Beam. It does a great job of explaining these concepts and then mapping them to Beam, similar to what I'm doing in this talk. They've been extremely helpful as a resource, and I would highly recommend checking it out if you want to learn more. Thank you.